Welcome to more trig substitution examples. So for this example, let's evaluate the indefinite integral, which is the integral of the square root of x squared minus 16 all over x dx. So if we look at this here, we have our x squared minus something case. So this lends itself towards the hypotenuse being our x. So we have our triangle with a hypotenuse of x. 16 is 4 squared. So our A here is 4. We will set that as our adjacent is 4. And the opposite will be that square root x squared minus 16. Using our x and 4, that relationship is secant. Let me update my screen quickly. So we have secant of theta is equal to x over 4. That means that x is equal to 4 times secant of theta. And dx is 4 secant theta tangent theta d theta. For our substitution involving that square root x squared minus 16, we have tangent of theta is equal to the square root of x squared minus 16, our opposite, divided by 4, the adjacent. So at this point, we have all the information. Oh, from there, we can solve for our square root. We get square root x squared minus 16 is equal to 4 times tangent of theta. And at this point, we have all the substitutions that we need. So from here, we go ahead and substitute. So we have our integral of the square root x squared minus 16 over x dx is that square root x squared minus 16 is 4 times tangent of theta. So we have the integral of 4 times tangent of theta divided by x is 4 secant theta. So we will divide through by 4 secant theta. And then we multiply by dx was 4 secant theta tan theta d theta. So we have times 4 secant theta tan theta d theta. Canceling out, this simplifies to the integral of 4 times tangent squared theta d theta, or 4 times the integral of tangent squared theta d theta. This one we're going to go ahead and convert into secants. So we will use the fact that tangent of theta, tan squared of theta is equal to secant squared of theta minus 1. So we are now looking at 4 times the integral of secant squared theta minus 1 d theta. At this point, we know our integrals. So let me give myself a little more space here. Again, we know the integral of secant squared. Secant squared just goes to tangent. So we have 4 times tangent of theta minus 1 d theta just integrates to minus theta. So that 4 is multiplying the entire tan theta minus theta, and then we have plus c. At this point, we substitute back in. So we had our relationships. We have the tangent of theta is the square root of x squared minus 16 over 4. We also had that secant of theta was equal to x over 4. That means that theta is equal to secant inverse of x over 4. And so we can rewrite our final answer as 4 times, in parentheses, square root of x squared minus 16 all over 4. And then still inside the parentheses, minus secant inverse of x over 4. And the parentheses, and then plus c. Let's go ahead and do one more example. Let's evaluate the definite integral from 0 to 1 of 1 over 9 minus x squared dx. So this one, we don't have a square root, but note that 9 minus x squared is the square of the square root of 9 minus x squared. As long as x is between -3 and 3, right? So this is for absolute value of x less than or equal to 3. We have this hold true. So what we are going to do is we are going to act like we are working with that square root of 9 minus x squared. So we have, in this case, if we're working with the square root of 3 squared minus x squared, that means this is the case where our hypotenuse is that 3. So if we draw our triangle, we have 3 for our hypotenuse. Our opposite side is our x. Our adjacent is that the square root of 9 minus x squared. The relationship involving the x and the 3 is our sine relationship. So we have sine of theta is x over 3. That means, of course, that x is simply 3 sine of theta. And we also have that dx is 3 cosine of theta d theta. So we have our substitution for dx, we have our substitution for x. The substitution involving that square root 9 minus x squared. We are looking at the relationship between adjacent and hypotenuse, so we can use cosine of theta. So cosine of theta is that square root of 9 minus x squared. Then the whole thing divided by 3. And we get that square root of 9 minus x squared is 3 cosine of theta. At this point, we substitute in. So substituting in, we are looking at the integral from 0 to 1. Once we do, so we'll have our integral from 0 to 1, 1 over 9 minus x squared dx is equal to, we have our integral from something to something of 1 over 9 minus x squared is 3 cosine of theta is the square root, so that whole thing squared will give us 9 minus x squared. Then we multiply by dx was 3 cosine theta d theta. We have a choice here. We can either convert the bounds now, or we can solve for them later. I'm going to find the antiderivative in x and then plug in the bounds at the end. So let's first just find the antiderivative. In x. So we are looking at, we have the integral, indefinite integral of 1 over 9 minus x squared dx is equal to the indefinite integral. One of our 3 cosine thetas cancels out. And so we are just left with a 1 over 3 cosine theta d theta. This is better known as 1/3 times the integral of secant of theta d theta. But we do know the integral of secant theta. So this becomes 1/3 times the natural log of the absolute value of secant of theta plus tangent of theta. We technically have a plus c on the end. At this point, we will go ahead and plug back in our secant of theta is hypotenuse over adjacent. So that's 3 over the square root of 9 minus x squared. Our tangent of theta is opposite over adjacent. So that is x over the square root of 9 minus x squared. And so we wind up with our indefinite integral is equal to 1/3 times the natural log of the absolute value of 3 over the square root of 9 minus x squared plus x over the square root of 9 minus x squared, and absolute value, and plus c. We can pull the same trick we pulled previously. This is 1/3 times the natural log of the absolute value of 3 plus x over the square root of 9 minus x squared and absolute value plus c. We can split division inside the natural log as subtraction outside. This becomes 1/3 times the natural log of the absolute value of 3 plus x minus 1/3 times the natural log of the absolute value of the square root of 9 minus x squared and plus c. Natural log of a square root, we can pull out that raising to the 1/2, pull it out front. This is the same as 1/3 of the natural log of the absolute value of 3 plus x minus 1/3 times 1/2, or minus 1/6 times the natural log of the absolute value of 9 minus x squared plus c. We can simplify further if we like. This is 1/3 times the natural log of the absolute value of 3 plus x, minus 1/6 times the natural log of the absolute value of 3 plus x, 3 minus x, plus c. We can then split that last one. This becomes 1/3 times the natural log of the absolute value of 3 plus x, minus 1/6 times the natural log of the absolute value of 3 plus x, minus 1/6 times the natural log of the absolute value of 3 minus x, plus c. And we get positive 1/6 times the natural log of 3 plus x, minus 1/6 times the natural log of the absolute value of 3 minus x, and then plus c for our antiderivative. From here, we can go ahead and find the definite integral. So we were looking from 0 to 1 of 1 over 9 minus x squared dx. We have an antiderivative of 1/6 times the natural log of absolute value of 3 plus x, minus 1/6 times the natural log of the absolute value of 3 minus x, evaluated from 0 to 1. This becomes 1/6, the natural log of 3 plus 1 is 4, minus 1/6 times the natural log of 3 minus 1 is 2. Then we subtract off 1/6 times the natural log of 3, minus 1/6 times the natural log of 3. This just winds up being 1/6 times the natural log of 4, minus 1/6 times the natural log of 2. Now, if you wanted to, we could rewrite this as 1/6 times the natural log of 4 divided by 2, otherwise known as 1/6 times the natural log of 2. So this is one way we can go about finding our definite integral. In this case, I went all the way to the antiderivative in x and just did my fundamental theorem of calculus in x. So again, this were a couple more cases of finding integrals using trig substitution. In the next video, we will look at cases that require some completing the square before we do our trig substitution.